Hello, today we are going to start a new chapter, the free electron theory of metals. So in this chapter we are discussing on metals. Okay, so there are classical theory and quantum theory as well for this discussion of metals. Classical theory means in classical theory the kinetic theory of gases and Maxwell-Boltzmann distribution functions are used. Whereas in quantum theory, the electrons or the electrons in the metal or free electrons in the metals are considered as the fermions. That means it obey Fermi-Dirac distribution function and or Fermi-Dirac statistics and Pauli exclusion principle. So if we consider Pauli exclusion principle and Fermi-Dirac distribution for the distribution of electrons in the metal or the distribution of electrons in the metal energy levels, so we are talking about the quantum theory of metals. There are classical theory and quantum theory. Here, this classical theory, in classical theory, the distribution of electrons are based on the Maxwell-Boltzmann distribution. And since this is electron gas, you can use kinetic theory of gas also. Kinetic theory of gases. Whereas in this case, here the electrons are Fermi particles, therefore Fermi-Dirac distribution function. Fermi-Dirac distribution. Okay. Also, it obey, since they are fermions, they obey Pauli exclusion principle. No two fermions are seen with the same quantum number. No two electrons can occupy a single energy state. The classical theory is also called Drude-Lorentz theory. Drude-Lorentz theory. So we are not going to discuss this theory here. So the Drude-Lorentz theory succeeded in explaining the Ohm's law. Ohm's law, that means, the current density is proportional to the electric field. So this is explained by the classical theory, and also it explained the ratio of the thermal conductivity to the electrical conductivity is proportional to temperature. That this is called the Weidmann-Franz law. So Drude-Lorentz theory explained Ohm's law and Weidmann-Franz law. And the classical theory could not explain the heat capacity and the magnetic properties, magnetic susceptibility of free electrons in metals. It could not explain this. So obviously we have to go for the quantum theory. So we are discussing the quantum theory of metals in this chapter. It is called the Sommerfeld theory of metals. Now, what are metals? According to free electron model, the valence electrons in the atoms of the metals become conduction electrons, and these conduction electrons are free to move within the volume of these metals. Thus, all the metals contain free electrons. This is called gas of electrons. These are like molecules in the gases. They are free to move within the volume of this metal. Okay. The simplest metals are alkali metals. Alkali metals means the first group, that is lithium, sodium, potassium, cesium, rubidium, etc. So these have the valence electron in the s orbital. That is, this Li has the electronic configuration 1s2, 2s1. Sodium has 1s2, 2s2, 2p6, 3s1. Similarly, the potassium also have uh, valence electron in the s orbital. Therefore, these alkali metals have one free electron per atom. Okay. Okay. Now first let us start discussing on the free electron gas in three dimension using the Sommerfeld quantum theory of metals. Free electron in three dimension. Three dimension. Okay. Sommerfeld free electron theory of metals. Consider a metal in the form of a cube of dimension L. Okay. So there are n number of free electrons, n number of free electrons in the cube. Therefore, we can write the free particle Schrodinger equation. For these electrons, that is h cross square by 2m, where m is the mass of the electron, into partial d square by h square plus square by dy square plus d square by dz square of psi of r is equal to E psi of r. So this is the Schrodinger equation. If the particles are confined to the volume of this metal, these free electrons are not free to move outside. It is free to move only inside. Therefore, the particles are only seen inside this cube. So the probability of finding the particle outside is 0. So this is the boundary condition. If you apply this boundary condition, the wave function at the boundary should be 0, because wave function outside is 0. Therefore, we know that wave function should be continuous. Wave function should be continuous. That means that is psi of 0 is equal to 0, and psi of L is equal to 0. If we apply this boundary condition, we can write the wave function as a standing wave. That means wave function psi of r is equal to a sine nx pi x by L into sine ny pi y divided by L into sine nz pi z by L, where nx, ny, nz are the quantum numbers in x, y, z direction. X, y, z are the coordinates of the electrons within the volume of the cube. L is the length in each dimension. Okay, this is the wave function of the free electron in the metal. Okay. We can consider a periodic wave function also. Here, when we are considering periodic wave function, like in the case of phonons, we have considered a periodic wave function as well. Then we can write psi of x is equal to psi of x plus L. Similarly, psi of y is equal to psi of y plus L. If we are considering a periodic wave function, okay, periodic wave function. So if we are considering a periodic wave function, the wave function is equal to a e raised to I k dot r, where k is the wave vector and it has where k is kx, ky, kz are the components of wave vectors. Therefore, kx should be is equal to 0 plus or minus 2 pi by L plus or minus 4 pi by L etc. Okay. So these are the components of wave vector. So these are the allowed values of kx. Substituting the value of this wave function in the Schrodinger equation, we get minus h square by 2m partial d square by dx square plus square by dy square plus d square by dz square of a raised to I k dot r is equal to e raised to I k dot r, where vector k is the wave vector of the electron, is kx I plus ky j vector plus kz k vector. Similarly, r is equal to xi plus y j plus zk is the position vector of the electron. Therefore, if we apply this thing and differentiate twice, we get minus h cross square by 2m I k whole square e raised to I k dot r is equal to e raised to I k dot r is equal to e raised to I k dot r. So this is nothing but h cross square k square by 2m is equal to, so therefore energy is equal to h cross square k square by 2m. Also we get this thing, we know that momentum is equal to h cross k, momentum operator, using operator method, p is equal to h cross k. Therefore energy is equal to, for free particle only kinetic energy is there, energy is equal to p square by 2m h cross square k square by 2m. So this is also another method for this. Okay. So anyway, h cross square k square by 2m is the energy of the free electron inside the metal. Also we can write h cross square by 2m into kx square plus ky square plus kz square. So we get this expression. In the lowest energy level, that means in the ground state, all the lowest states are occupied, all the lowest levels are occupied by the electrons, free electrons. That means the uppermost energy is called Fermi energy. Okay, so all these levels are occupied by electrons. Energy of the uppermost electron is called the Fermi energy. Okay, or in k space we can represent the allowed levels. All these levels are occupied by the electrons, and in k space this is kx. This is a particular, this is the value of k, which is equal to, in k space it is represented by a sphere of radius k. So this k is called kf. In ground state this k is called kf. Therefore the Fermi energy is equal to, Fermi energy ef is equal to h cross square kf square by 2m. Okay. Here ef is the Fermi energy and kf is the Fermi wave vector. We know that the number of levels, number of states within a range of delta k or delta kx equal to 2 pi by L is equal to 1. So inside a volume of 2 pi by L whole cube, there are one allowed level. So one level, one allowed state, one allowed state per 2 pi by L whole cube. Okay. So therefore, the number of allowed states Therefore, the number of allowed state is therefore the number of allowed levels per unit range of k is equal to L cube by 2 pi. Okay. So therefore, what is the total number of allowed states? Within the sphere of Kf. Of radius of Kf. So this is equal to 4 by 3 pi Kf cube into L cube by 2 pi. Okay. So these are the total number of allowed levels within the sphere of radius of Kf. So 4 by 3 pi Kf cube is the volume of the Fermi sphere, and L cube by 2 pi whole cube is the number of allowed levels per unit range of K. Okay. Total number of electron states. Total number of electron states. Okay. Within Fermi surface. Fermi surface means the sphere of radius Kf. Okay. So this is equal to 2 times 4 by 3 pi Kf cube into L cube by 2 pi whole cube. Here this 2 is because in each state there are two spin levels are possible. So one up state and down state. In each state there can be two electrons with a up spin and down spin. So they have slightly different energy. So therefore ultimately there is no electrons are with the same single energy level. Okay. This is equal to L cube. Here L cube is the volume of the cube, that is volume of the metal. V divided by 8 get cancelled. Pi cube is there, so pi square, 3 is there. So 3 pi square, V by 3 pi square into Kf cube. So this is the total number of electron state within Fermi energy surface. Okay, Fermi surface. Okay, in ground state, all these states are occupied by electrons in the ground state. N is the total number of free electrons. So therefore, this is equal to N. So therefore, we can write N is equal to V by 3 pi square Kf cube. Therefore, Fermi wave vector Kf is equal to 3 pi square N 1 by V. So this is equal to Kf is equal to this raised to 1 by 3. So the Fermi energy EF is equal to H cross square Kf square by 2m is equal to H cross square by 2m into Kf square is 3 pi square n by v all raised to 2 by 3. 3 pi square n by v all raised to 2 by 3 is the Fermi energy. Okay. So Fermi energy expression we have already derived this in the statistical mechanics class. Here h cross is the Planck constant. It is 1.05 into 10 to the minus 34 second, and mass of electron is 9.1 into 10 to the minus 31 kilogram. If you substitute these values, you get the energy in electron volt as 3.65 into 10 raised to minus 19 n raised to 2 by 3 electron volt. This much electron volt. Okay. So here n is equal to the number density of free electrons. So free electron number density. Generally, the Fermi energy is of the order of few electron volts. Okay, in metals. For me, momentum is equal to h cross kf, which is equal to m into Fermi velocity. So Fermi velocity is equal to h cross kf by mass of electron. This is equal to h cross by m into kf is 3 pi square n by v, or n all raised to 1 by 3. So this is the Fermi velocity. Fermi velocity can be found like this. And also you can find out the Fermi temperature. So this is equal to, Fermi temperature is, EF is equal to K into TF. So you can find out TF is equal to EF divided by the Boltzmann constant. Okay. So from this you will get the Fermi temperature. Now the density of states of electron. Okay. Density of states means number of orbitals per unit energy range. Unit energy range. Okay. So density of E is equal to dN by dE. The density of state is the total number of states per unit energy. So total number of orbitals with energy less than, this is equal to n. N is the total number of orbitals now. Okay, which is the maximum number of particles which can occupy. So n is equal to p divided by 3 pi square into k cube. Okay. But we know that E is equal to p square by 2m is equal to h cross square k square by 2m. Therefore, k is equal to 2m e divided by h cross square. Okay, all raised to 1 by 2. So therefore, we can write this total number of orbitals is equal to v divided by 3 pi square 2m e divided by h cross square whole raised to 3 by 2. Okay. So this is the number of orbitals with energy less than E. Therefore, density of states is equal to dN by dE is given by V 3 pi square 2m by h cross square whole raised to 3 by 2 into 3 by 2 e raised to 1 by 2. Okay. So this is equal to 3 get cancelled. V divided by 2 pi square 2m by h cross square whole raised to 3 by 2 e raised to half. So this expression we have already discussed in the statistical mechanics. There we have used G, statistical weight factor, for electron. Okay. So if you multiply, you will get the same expression here. Density of states. In statistical mechanics, we have studied this thing as this is equal to 2 pi v by g into 2 pi v by h cube 2 raised to 3 by 2 e raised to half. So this is the same expression we obtained in statistical mechanics. Here g is equal to 2, v is the volume 2 pi by h cube. Here h cross cube is there. So if we is the density of states in 3 dimensions.